Okay, so today we're going to be talking through the integral method example for the energy part of the equation. Last time we did the momentum part, and we came up with a model where we were just taking our kind of standard boundary layer and developing an integral solution for that. So we threw away things like advection across the surface, some other terms that, like, it wasn't shear driven, so there's the shear stress at the outer boundary was 0, and so we set up a model, compared that model, and I guess we could look back. We said, with our integral solution model, assuming a quadratic velocity distribution, we came up with a friction coefficient relationship, which was 0.73 over Reynolds, and then comparing that to the self-similar solution, which is an exact analytical solution, which that gives us 0.664. That says, okay, we can do pretty well with our quadratic. We could even do better if we had a third-order polynomial, or worse if we had just used a linear model. So again, we can do the same thing for energy, and we'll go through that. The steps for the energy part of it are really similar to the momentum part. Right? We are assuming a functional form of temperature. So again, we have to say we're going to impose this temperature distribution. It is the temperature distribution for the problem. We assume that functional form, and then we solve for the unknown coefficients that go with that form. Substitute that into the integral forms of the boundary layer equation. That's going to lead us to an ODE, hopefully in terms of delta T, right, our boundary layer, our thermal boundary layer thickness. We solve that to find delta T. And then the boundary layer thickness gives us something that we care about. So normally heat transfer coefficient, or Nusselt number, for the thermal boundary layer. Okay, so let's go through how we would do this for the velocity profile that the temperature profile that we want to assume. So let's, like the velocity profile, we need to say, I have some temperature profile. So my temperature profile is going to be a function of y over delta T. But I guess I want to define temperature so that it's 0 at the boundary, at the surface, and 1 at the edge of the boundary layer. So I'm going to do this normalized temperature. And that would be T. So T is my temperature as a function of y. I guess we could say T of y minus Ts divided by T infinity minus Ts. There's a normalized temperature. By definition, it's going to be between 0 and 1. There's nothing in this that's going to I suppose if you had a lot of viscous dissipation, you might have heat generation and stuff like that, but we'll throw that away. We'll say our Eckert over Reynolds number is small, throw away viscous dissipation. So this number for most problems is going to be between 0 and 1. So we need to assume a functional form for that. Let's assume that the functional form is similar to the velocity, which was a plus b times y over delta t plus c times y over delta t, that quantity squared. This is our second order quadratic model. You don't have to assume the same thing for temperature that you did for velocity. We could do something different, but it just makes it, I think, you see the process, it's sort of similar, and it saves us a little bit of work. So we'll assume the same form. So our job now is to impose conditions on this that are going to let us specify A, B, and C. So conditions. There are, again, a sort of arbitrary number of conditions that you can come up with. We will put 4 of the most common ones, probably in their order of frequency. So the first would be, I guess you'd call no slip at the surface. But what that really means is T at y equals 0 is equal to Ts. So no slip is really saying, yeah, if you have velocity that's 0 between a fluid and the adjacent surface, the molecules of the fluid are right next to the molecules of the surface. They're not moving. So you're going to have the fluid temperature at y equals 0 equal to the surface temperature, right? So it sort of follows from no slip, but it's a weird way of saying it. Second condition would be the free stream temperature is recovered. at t y equals delta t is equal to t infinity. And so temperature at the edge of the boundary layer is equal to T infinity. That would be the second common one. The third one would be related to heat flux. So heat flux at the boundary layer is recovered. So that's saying my partial of temperature with respect to y, or say like minus k times that, which would be another way of saying q dot double prime at y equals delta t is equal to 0. This left-hand side would be evaluated at y equals delta t. So Fourier's law here, or the term we define for that, is equal to 0. Last thing would be the x-momentum energy form of the x-momentum equation would be satisfied. So energy form of x momentum is satisfied. And I guess we could do that anywhere again, but let's say at the surface. So that would look like rho times c times u partial t with respect to x plus v partial t with respect to y is equal to k second derivative of temperature with respect to y plus mu times partial u dy. Do that again. Partial u partial y squared. So that whole thing, evaluating that at y equals 0. So we're enforcing that to be true. So again, like we have our three coefficients, I guess what we can do is we'll go through, pick some of these in no particular order. I guess we'll pick the first three and enforce them. So no slip, that is t is defined at the surface, t is defined at the edge, and then we're saying no heat flux at the edge. So if we do that, it follows exactly the same steps as we did before for the velocity, so we won't repeat it. But if we do that, you end up with the equation that is written on the next slide, this one up here. So we have the temperature in non-dimensional form is equal to 2y over delta t minus y over delta t squared. So we have our temperature related to the thermal boundary layer thickness. Again, the same thing as before. If we went through and we said some of those terms were not important, I guess actually we should be, let me go back one. Let's be careful here. So what are we throwing away here? We are throwing away viscous dissipation. We are saying q dot at y equals delta t is 0, so that goes away. We are also in this problem saying there's no velocity at the surface. Okay, so if we make those assumptions, first we've solved for the velocity using the first three. We get the velocity equation that's shown here. And then from that, you can also write out an equivalent statement for heat flux at the surface, and then apply that in the integral equation that we just simplified. Okay, questions on this so far? Okay. So what does this look like? The solution, again, going from 0 to 1. So this is our, what is this? Dimensionless distance from the surface. So y over, I don't know why that doesn't render. It's y over delta t. And then our dimensionless temperature difference. So as you go up in height, this would be your temperature. You're seeing it's sort of starting off with a higher dt dy. And then as you get out to the surface, it's or out to the edge of the boundary layer, it sort of tails off. But it follows the same kind of approach as the velocity. Linear is the least accurate. Quadratic and cubic get better. And then the known solution is shown here.